Is my screen showing?
Yes, please. But I need to zoom in so that
It's
we can see. Yeah.
okay, but it's not showing at your end, is it? Is it?
Is it? Is it? To show you.
It is right. Okay, so memory systems is showing. Okay, all right. Once again, um, my name is Caleb Ahenakwa, and I'm representing Group One. And so we are going to speak about memory systems. And so, as you can see from our outline, we'll define what a memory system is. We'll then
Can,
define
can
what a
you put
primary
your
memory is.
presentation in the, hello? Kindly use the
Yeah, I
presentation
can hear you,
mode.
sir. Hi, sir.
Kindly use the
Okay,
presentation
sure,
mode.
sure. All right. Sure, sir. Okay. I have the presentation mode now. And so
But,
I'm
but
just
it's not
getting that
showing.
to show. Okay.
Okay.
Is it
All
showing
right.
now?
Okay, it's loading. It's
All
loading.
right.
Yeah, that's fine. Yeah, go ahead,
All right.
please.
Sure. Okay. So,
But can
all
you
right. So
introduce
once
your
again,
members? Can you
sure,
please
sir, I'll be
introduce
doing
your
that.
members?
Okay.
Let's see whether they
All
are
right.
here.
Sure, sir. I'm doing that. So just jumping right into Group One, these are members. We are so this is not the main document. I was opening the main document, but I had a challenge with it, so I'm using this from my Google Slides. And so we have quite a number. We're over 20 of our group members here, and Andrew Scoffy, who is our group leader. So Andrew Scoffy is one of our members. Then myself, Caleb Ni Ajete Ahenakwa, and then we have Adamte Joel, and we have Eric Enyonam Adigbo, and then we have yes. Are they supposed to show their faces or show their raise their hands that they are here?
You skip that. When you are done with the presentation, we'll check the attendance so that we don't waste time. So you go ahead with your presentation.
Okay.
Okay. Yeah.
All right, that's fine. Okay, sure, sir. Okay. What we'll be talking about today, we'll be having an outline of what a memory system is, what a primary memory is, what a cache memory is, what a virtual memory and secondary storage is, and then there is the summary and comparison. And so, essentially, when we say a memory system, we are looking at that part of the computer that stores data, and so the computer can work properly and quickly. And so, we give an example beneath the definition of what it is. Okay, we're trying to compare it to how the brain works. Essentially, we all have brains. And just like we have brains, computers do have brains. And that part of the brain of the computer is the RAM. And that particular part of that brain remembers things. Just like we also have memories, we recall certain things. And so in that part of the computer, it has that brain that remembers things. It also has a storage that keeps information. And it also has what we refer to as a cache that quickly works on how things how it could work faster. So as far as what a memory system is, this is what it does. Now we move on to that part of a definition of a primary memory. being the random access memory. Now, if you recall from other group presentations, when we say a RAM, RAM, it's essentially a random access memory. And per its definition, we can say that a random access memory stores data temporarily. Now, here is where it gets interesting. Now, again, we compare to a memory to that of the brain of human beings. Now, unlike us, we don't temporarily remember things, although some people forget, we at least remember for a while. But for that part of the brain of the computer, the random access memory is temporary. It only stores data while the computer is on. And until you turn that computer off, all of that data is lost. And the random access memory is that part of the computer that is used to run active programs and open files. And so you do also know that when you're buying a computer, there's what we call the 16 gig RAM, 8 gig RAM, 32 gig RAM. So it's very essential these storages are there because when you're working with heavy programs, that computer needs a lot of memory to be able to work on it. So the 32 gig, 16 gig RAM is to allow for heavy programs to work. So if you have an 8 gig RAM, your computer will work all right, but then it gets to a certain point where it might freeze or it might be difficult to load certain programs. That is because it has exhausted that bit of the memory. So that is what we refer to as the random access memory. And we put over here that more RAM is equal to more apps that can run at once. Going back to the example I gave as regards why a computer needs more memory. So these days, a lot of programmers are going for 16 gig RAM rather than 8 gig RAM because they run on heavy programs. So we wanted to run an experiment here where we open Zoom, WhatsApp, and Chrome together. When you open all these three together, if your computer doesn't have a good random access memory, your computer might freeze, but well, I have a good computer, so I'm able to open Zoom, I'm able to open WhatsApp, I'm able to open Chrome. Some people still use 4 gig RAM. So if they were opening all these things at the same time, it will take a long time for these programs to work. Okay, so the important note we have here is while typing an assignment, I'm unable to see. Okay, while typing an assignment, your work leaves in RAM. If power goes off before saving, everything is lost. So it's important that you have a good connection to ensure that you don't lose anything. So we move away from what a random access memory is and move on to another part of the primary memory of the computer called the read-only memory. Now we've already, introduced you to what a random access memory is, and now we have the read-only memory. This is the kind of memory that is permanent. Again, using the comparing it to human beings, we have the read-only memory. Some people can forget, but at least we have the read-only memory where we don't forget things. That is why when we study, we are able to remember. So that part of the computer also has a read-only memory, and this is what stores the boot instructions to start the computer. So a computer is only able to start properly because of the read-only memory and because of the instructions that have been written on it. Now, data in read-only memory cannot be changed by users, and we said it is found in firmware of phones, laptops, and devices. So we give a real-life experience here. Okay, when you press the power button, the laptop starts automatically, even after the battery dies. It still boots. That process is called it uses the read-only memory. So we try to give a clear example here to help you remember. Again, when data is off, the difference between RAM and ROM is when data is off, your RAM is lost. When your data is off, regardless of whatever has happened, your read-only memory retains. Again, a difference between RAM and ROM is data is temporary, and for ROM it is permanent. The main use of RAM is to run programs. A lot of the software you use relies on RAM, and the boot system of your computer relies on ROM. So we move away from that to talk about a cache memory. It's a very interesting part of the computer. Why do I say so? Because it's very fast memory that stores frequently used data, so the CPU can access it quickly, reducing delay. Let me give a clear example of, for instance, okay, so whenever you use your phone, okay, every program you open has a cache file. So it utilizes cache files. So sometimes your phone can be very full. with a lot of, data. You clear your read-only memory, your storage to see what, but still, there's still, some data being used. When you go to your app, you can clear your cache files. And the cache file is the fastest part of the memory. It is faster than the random access memory. It is closest to the central processing unit of the computer. The interesting thing too is it's smaller in size, and it also stores frequent data. That is why I was giving you an example of it keeps recently or often used data. So every app you use makes uses of cache file. It also then improves the speed. So your RAM will still be used when your computer is working, but the central processing unit checks cache before going to RAM. So the cache it works hand in hand with the central processing unit, although the other parts of the computers will still be used. The other memory parts of the computers will still be used as a random access and a read-only memory. Now, we also have what we call a virtual memory. And now a virtual memory is a technique where the computer uses part of the hard drive, the SSD, as extra RAM when the RAM is full. So when you open many apps, like I already indicated, your RAM gets full. It gets really full. And some software really eats RAM. I don't know if you've heard of this language. They eat RAM. They eat a lot of that data. And so when that happens, your computer, because it doesn't want to, freeze on you or leave you disappointed, it accesses a hidden storage. That storage we don't see, but that storage it borrows that storage from let me say the SSD or the HDD, so the system can stay running. So your 8 gig RAM can be full, but still your computer is working all right, and you think, yeah, you have a good computer. Yeah, you have a good computer, but it's also trying to save you time by borrowing data from the HDD and SSD. That is where the virtual memory comes in. So your computer may stay active because your computer has that sense to be able to, borrow some space. So it is not, as we put here, the random access memory is not real RAM. It acts like it's using storage space. It is slower than RAM, and it activates only when RAM is full, and it helps to prevent system crashes when memory is low. So, like I said, think of it as an emergency memory, extra help when your RAM is tired or when your apps have utilized all the space. Now, we move on to another interesting part of our discussion, what we call our secondary storage. Now, secondary storage permanently holds data even when the computer is off. It's used for long-term storage of files, programs, and the operating system. So back in the day, computers used to run on HDD. They still run on HDD, but if you want a very good PC, you go for the solid state drive, which is the SSD. This is very, very, very fast. There are no moving parts, and it's very durable. Again, another example of secondary storage can be your pen drive, which we refer to as the USB. And, you can still use SSD. Comes in external parts, so you can still carry an SSD around. And these days, computers don't come with the CD side, but, some places still make use of CDs and DVDs, which is used for backup. So when we say secondary storage, it's essentially the external part of the computer. Okay, sometimes it can be external, but inside a computer. Okay, so HDD, SSD, these are all secondary storage. And if you want to store your movie, you put it on these things. You store your files, your pictures, your documents. All of this are stored on the secondary storage. And so for secondary storage, data is kept even when it's off. So you realize that even when your computer is off, you have downloaded a file somewhere on your computer, you can still access it. That is a good thing about secondary storage. It stores the operating system. If you are running a Linux operating system, when your computer turns on, it remembers it is on Linux. If it is running on Windows, it remembers it's on Windows. That is how come it stores these operating system files and it stored apps. But the interesting other good thing, the other bad thing too is it is slower. If you have used an external hard disk before, you realize that sometimes when you're putting a file on it, it can take a long time. An SSD might be relatively faster, but it's very slow with, a lot of these secondary storage devices. So that is what we refer to as secondary storage. And so a summary, since we have gone through a lot, just to help you remember, we have introduced you to a memory system referred to as RAM and ROM, cache, and virtual. As you can see from the presentation, we place them under speed, capacity, volatility, and primary use. As far as speed goes, and we do know that cache file is the fastest. The closest to the cache file is the RAM, random access memory. So just to help you remember, if you are asked, which part of the memory is faster, always remember that the cache file is the fastest. If you are asked which of it is volatile, the downside to a cache file is it is very volatile. And a random access memory too is very volatile. When we say volatile, it means that it only works, when the computer is on, but when the computer is off, you lose everything. Okay, so the primary use of it, again, to help us remember, a random access memory is used to run active programs. A read-only memory is used to boot or firmware instructions. A cache file is used to speed up CPU access. And a reminder that it's that part of the computer that borrows extra data when you have exhausted your RAM. So this is the end of our presentation. And at this point, if you have any questions, you can bring it to our attention and we'll do our best to respond to it. Thank you so much for your attention.
All right, thanks a lot. Colleagues, do you have any question for them? Hello? Hello?
Hello.
Yeah, do you have any question for them? For them?
Hello, Doc.
Okay. Yeah, yeah.
Yeah, so this is Justice. I want
Okay,
to
Justice, go
find
ahead.
out the difference between the SSD and the RAM. He made mention of SSD being non-moving parts. Is it not the same as the USB? So what are the clear difference, the difference between the RAM and the SSD?
Okay, so an SSD is part of the secondary storage. There's clearly a difference. The RAM is, when your active programs are working, and SSD is the RAM is volatile. That means once your computer is off, you lose every part of the data. And the purpose of the random access memory is just a temporary working memory for your computer. Okay, but the purpose of the SSD is to act as a permanent storage. Okay, now what the random access memory does is it holds data when your system is actively using apps, files, and processes. But what the SSD does is it stores your operating system, it stores the apps, and it stores the files long term. Another difference is the RAM is extremely fast. The SSD is also fast too, compared to HDD, but the RAM is obviously faster. You understand? And as far as volatility concerned, I've already said that the random access memory is volatile, and which means that your data is lost when power is off. But your SSD, your data stays on when the power is off. For example, let me give an example. When you open Google Chrome or edit a document, it runs in random access memory. But when you installed Windows 11 or you save photos on your SSD or you save photos, it goes on your SSD. So they perform different roles. Okay, so think of SSD as like a filing cabinet. It keeps everything stored even when the computer is off. And you can think of RAM as let's say your desk space. Okay. The bigger desk space you have, the more tasks you can handle even smoothly. Does that answer your question, please?
Right. Sure. So I have a
Thank you.
follow-up question in that regard.
Yeah.
Okay, so you made mention of secondary storage device, which are the SSDs and the USBs. Yeah, so for the SSD, is
Yeah.
indicated that
Yeah.
they are non-moving parts. Likewise, the
Mm.
USB. So I just want to know what is the difference in terms of performance, speed, and kind of data access between the two storage devices that we have mentioned, the
Okay, as in you are
SSD
looking
and
at
the
this.
USB. Yes.
Okay.
Like there are
All right.
two storage devices. One,
Right.
they are both having no moving parts, which as compared to the HDD.
Mm.
So what is the difference between the SSD in terms of performance,
Right.
speed to the USB?
Okay, so the difference is they also have a difference in as much as they all fall under secondary storage. So USB and SSD fall under secondary storage, but they all have differences. Okay, and the difference being that the SSD is much faster. Especially if you want to read or write large files for running most of your programs. And the SSD was designed for a lot of high performance. Okay, and if you randomly do a quick Google search, okay, the speed of an SSD is around 400 to 3,500 megabyte per second. But a USB's typical speed is 20 to 400 megabyte per second. That means an SSD is way, way faster. That is the typical speed at which they operate. All right. And if you look at proper performance, a USB is pretty much good for transferring just files. Okay, but you cannot, boot your operating system quickly without an SSD. So the SSD is what your computer relies on to boot the operating system quickly. But the USB, there's no way that you can use it to boot because it's external. The SSD can be external. You can still take your SSD out and place it in a container. But your computer actively works, by working on the SSD, what is inside the computer. In as much as it's internal, you can also make it external. But essentially, an SSD runs faster. It's been designed to perform a lot of high performance. Does that slightly answer your question, please?
Very well, very well.
Okay. All right.
Thank you very
Thank you.
much.
Yeah, my brother, the name again, please.
So I'm Caleb Ahenakwa. Caleb.
Yeah, Caleb, great presentation. You did very well with the presentation, but you spoke about the cache memory. I was expecting the group to also talk about the various types, like the cache levels, the level L1, the L2, L3, and also some terminologies that applies to the cache, like the cache hit, the cache miss. Can you speak briefly on this, please? And why the cache memory is important?
Yes, sir. So I'm trying to, it is part of this documentary vehicle. I was struggling to open one particular document. And so I had to refer to my Google Slides. And so let me try and use what we put together and to explain what it is briefly. And so the levels of the cache memory, as you rightly indicated, and being the L1, L2, L3 is based on speed, is based on size, is based on distance. And all of this is from the core of the central processing unit. So each level balances the speed and the capacity. So the L1 cache, which is the level 1, is located inside each CPU core. And the L1 is the fastest part of the cache file. And compared to the L2 and L3, it is the smallest. Okay, and in terms of small size, it's typically between 32 kilobytes to 128 kilobytes. And the purpose of the L1 cache is to store the most frequently used instructions and data. And so it is the CPU's first stop when it is looking for data. Now you move away from L1 and move to L2. Now the L2 is also inside, or let's say very close to each core of the central processing unit. But the speed is slightly slower than the L1. And the size compared to L1, which is 32 to 128 kilobytes, the size for L1 is larger. And so you have a size of around 256 kilobytes to 2 megabytes per core. And the purpose of the L2 is also to hold data that isn't in L1, but it is still used often. So it's like a backup to L1. I don't know if you get it. So again, now away from L2, there's L3. Now L3, the location of the L3 is shared among all the CPU cores. And the speed is slower than L1 and L2, but it is still faster than the random access memory. Okay, and the size again compared to the L2 and L1, it is much larger. L2 is 256 to 2 megabytes. L1 is 32 kilobytes to 128 kilobytes, but L3 is 2 megabytes to 64 megabytes and beyond. And that means it is the bigger size. And the purpose of the L3 is to store data shared between, the cores of the CPU. And it usually helps a lot with, multitasking and performance, especially if you're using coding or programming. That is where it taps into the L3 because the performance needs to tap into the multi-core part of the CPU. So it helps with multitasking and a lot of performance that require a lot of memory. So this is the difference, L1, L2, L3. I hope I have done justice to defining it for you.
Yeah, great one. So can you also speak to the difference between catch hit and then catch miss?
Get the last term, the catch what, please?
Miss, catch miss, MISS, and then hit, HIT.
Okay, so well, let me just use the top of my head to try and see if I can break it down. And maybe I'll say that, okay, per the name, catch hit and catch miss. Maybe like a target it is missing and a target it is hitting. So maybe I'll say that when the central processing unit is looking for data, it first checks the catch before going to slower memory like the RAM. Like we've already established that the cache memory is that part of the computer. When your RAM is exhausted, it looks for extra storage. So maybe a cache hit per its definition could be when the CPU finds that data in the cache. And the result of a cache hit is, it means that it has hit the target. So it means that the access is very fast. Let me give a clear examples to say that, for instance, if you need a file and it's already on, let's say you have a table, you have a desk, your office, and if you need a file and it's already on your desk, you quickly grab it. For instance, you need a stapler on your desk, you quickly grab it. But in the other side, if the stapler is not on your desk, you have to go to another room to get it. That is where the catch miss comes in. So a catch hit is where the CPU finds data in the cache, but a catch miss is the CPU does not find the data in the cache. And so you must fetch it from the RAM, and the performance is usually slower. Going back to the example I just gave, so when it is not on your desk you have set up, if that stapler is not on your desk, you might have to go to the next office or go to another desk to get it. That is the comparison or difference I might try to make in defining it, please.
Excellent one. So that is it. I think you have clearly provided a distinction between the catch hit and then the catch miss. So once we request and we don't find it in the catch, then it means that that's a miss. Okay, that's fine. Colleagues, I think it's a great presentation. I'll not comment too much because I've not been commenting on the others. So I'll wait after everything, then I'll provide my comment. But you did well. Congrats. Let's see whether your colleagues are here. Can we do that very fast? So we take the next group, please.
Sure, sir. Let me just mention their names. They are here, and so I'll quickly mention their names. Andrew Scoffy, please, if you are here.
Yes, please, I'm here.
All right. So Andrew Scoffy is here, and Caleb Niajete Ahenakwa, that's myself. I am here. Francis Abel Amwakon, please.
Yeah,
Let's
I'm here.
see. Okay.
I'm here.
Right. Sheriff Shehu Damfulani. Sorry if I
I'm
didn't
here,
pronounce
please.
your name. All right.
That's
So
fine.
Sheriff
It's
is
okay.
here. Adamte Joel. Okay. Eric Enyonam Adigbo.
Present.
All right. Foster Emisa Nyanfo. Nana Kojo Anderson.
Present, please.
All right. Theophilus Mauvi Zigba. Joseph Merino. Emmanuel Frimpong.
I'm here, please.
Okay. Benis Dakwa. Benis, I think I saw Benis somewhere
Yes,
here. Benis.
I'm here, please.
All right. Abigail Osei.
I'm here, please.
Maxam.
Active.
Gloria Edufo.
Present.
Michael Tay Anongo.
Present.
Desmond, all right. Desmond McLean Amuzu.
Present.
Mark Kofi Akaho.
Present.
Henry Marvin Awume.
Hey, McLean, I'm here.
Oh, sure. Henry Marvin Awume. Prince Kwesi Owusu.
I'm here.
Gideon Enyan.
I'm here, please.
All right. So
Okay, so now we'll move
Okay,
on
thank
to
you.
group six.
Thank you. Let's move on to the next group, please.
Group six. If you can start your presentation.
And I hope they should try as much as possible not to just read to us, but you explain for us to understand.
Okay, good morning. My name is Rogers Delato. I'm representing for Group 6. Please allow me to share my screen.
Roger, please, there's a background noise. I don't know if it's on the side.
Okay. Good morning. So, as I said, my name is Rogers Delato. So I'm representing for Group 6. We are presenting on performance metric and evaluation. Okay, so after the presentation, I'll come back here for the group names. Okay, so performance metrics and evaluation is essential in computer architecture. They help us determine efficiently how a processor executes programs, support optimization, and guide its design choices. Our main goal is to improve performance while maintaining a balance between cost, power consumption, and system complexity. So this is a very big course. So we'll first of all look at clock speed. We'll look at clock speed, and then we also look at cycles per instructions, and followed by instructions count. Then we also look at the millions per instruction, and then the associate flops, which is floating point operations per second. Then we also look at the techniques where we will try to, or as a developer, will try to improve performance through their code or through their programs. So let's start with clock speed. We have to know, what we have to know is clock speed is the heartbeat of a processor. It measures how many operations a CPU can execute a program in a second. And it also dictates how quickly it can process instructions and move data from one component to another. Every CPU has an internal oscillator, or it's called clock. That internal oscillator generates pulses at regular intervals, and these pulses coordinate all the components of a processor. It is much like a conductor keeping a symphony in sync. So in computing, every component has to be in sync. Everything must stay synchronized. Computers generally run on clock beats. That is everything. If a component is not ready on time, the CPU has to wait. So a faster speed will not always mean better performance. A clock cycle is one pulse in which the CPU performs a basic task like fetching a data or doing addition or adding two numbers together. When it comes to measurements, clock speed is generally measured in hertz, which represents cycles per second. But because these days CPUs are very fast, so we use the gigahertz, which means a 3.5 gigahertz processor can perform about 3 billion cycles per second. One disadvantage or one disadvantage is that higher clock speed will not always mean better performance, as I have said earlier. When we are talking about performance, it depends on both speed and efficiency. Speed comes from the clock speed, and then efficiency is about how a developer performs some techniques with the help of the system architecture, perform some techniques to increase programs' performance. So we can say that clock performance is generally equal to clock speed times instructions per second. The instructions per second is all about efficiency over there. So instructions per second measures how much work the CPU completes in each cycle. So that is why a 3 gigahertz CPU can outperform an older 4 gigahertz one. The modern one does more work in a cycle than the older one. Okay, so to better understand clock speed, we will look at two terminologies or two concepts, which is cause and threats. We'll quickly look at cause and threats, which will help us to understand how clock speed works. So for us to move away from the brain of the computer, we'll take the analogy of a kitchen. Clock speed is like how much one person or one chef works in the kitchen. And then when we talk about cause and threats, they represent how many chefs are available and how many tasks they can handle at the same time. Generally, a core is a physical unit built into the CPU. Early CPU just had one core, but modern processors now have up to from 4 to 64 or more cores. So each core works like its own mini processor, capable of handling tasks independently. An 8-core CPU is essentially 8 processors working together. So when your computer is when you say your computer is an octa-core, it generally means your CPU, you have 8 processors working together to run programs. Just like you have 8 chefs in a kitchen working together to prepare a recipe. When we are talking about threads are like task managers. They are the logical counterpart of cores. So while a core is a physical hardware, a thread is a sequence of instructions managed by the operating system. Threads don't generally increase the speed of cores. Instead, they improve efficiency. If one thread is waiting for data from the RAM, the core can switch to another thread and continue working, which will reduce the idle time of the CPU. So let's quickly look at this table, which features the difference between cores, threads, and clock speed. Clock speed only represents the raw execution speed of a CPU. The better said, we can say the raw execution speed of one core. And then a core is the total workforce on the CPU, the total workforce which is built in on the CPU. And then thread is about what? It's talking about multitasking efficiency. Multitasking efficiency. If, let's say you have a computer, on your computer you have one core, let's say 10 gigahertz CPU, which is one core, that computer will be very fast at running a single program. But when it comes to, let's say you want to run a game, you are playing a game while you are streaming for music, at the same time you open like 50 Chrome tabs, that computer will start to get slowed down because the core is not building, it's only having one core. So, but with this one, the operating system will come with mechanisms which will make even a single core CPU can operate as a dual core. So we also look at that. Those are the performance techniques we'll look at. The analogy here is that a clock speed is just like one chef in a kitchen. How fast a chef can chop a piece of meal, or how fast a chef can prepare a piece of meal. And then the cores are how many chefs are in the kitchen, and then the threads are how many dishes a single chef can juggle. Okay, so let's move on. So we have already looked at clock speed, and then we use the cores and then the threads to explain the idea of clock speed. So let's look at cycles per instructions, or CPI. If calls are the chef and clock speed is how fast a chef works, then the CPI will measure how much effort it takes to finish a single recipe. So in computer architecture, the relationship between these factors is known as the iron law of processor performance. It is a balance between the speed, efficiency, and workload. So cycle per instruction will help us to distinguish between the efficiency and workload. For a CPU performance, the total time it takes to run a program depends on three key factors. We are talking about the instruction count. That is one factor. The cycle per instruction, that is another factor. And then we also talk about the clock speed. So the CPU performance or the CPU time. The CPU performance generally is about the time it takes for the CPU to run a program. And that particular performance, that performance depends on these three factors: the instruction count, the cycles per instruction, and then the clock speed. Instruction count is like how many instructions are there in a program. When we are running a program, the CPU will determine how many instructions are available. That is the instruction count. And then the CPI is about how many cycles each instruction will take. How many cycles each instruction will take. And then the clock speed is how fast the clock runs. How fast the clock runs to execute a single instruction. And these factors, they work together to determine the overall performance of a CPU. So the instruction count, we've been mentioning instruction count. So let's look at the instruction count or the IC. Instruction count is the total number of instructions a CPU must execute to complete a task or to run a program. So instruction count is mainly influenced by the compiler and the instruction set architecture. The instruction set architecture, we have two. We have the x86 and then the ARM. The x86 uses the complex instruction set computing. So the complex instruction set computing is about fewer instructions per task. But each instruction may take more cycles. So when a CPU runs on more cycles to execute a single instruction, it increases the CPI. And then the ARM is about reduced instruction set computing, which uses more instructions, but each one is simpler and executes in fewer cycles, which indicates lower CPI. So let's go back to the CPI again. Let's fully understand what the CPI means. CPI refers to the average number of clock cycles needed to execute a single instruction. So for engineers, the engineers who manufacture CPU, and their ideal target is CPI should always be 1.0, which means that one instruction per cycle. That means when the clock runs, in a cycle, one instruction has to execute. But we have techniques with the modern high-performance CPUs, the compiler and the RISC and the CISC. They can make the CPU perform multiple instructions in a cycle. So they use a technique called superscalar execution to effectively achieve lower CPI, which is lower than 1.0. So instruction count is measured, the CPI, cycles per instruction, is measured as IPC, instructions per second. So instruction count is measured as IPC. So instruction per second is just 1 divided by cycles per instruction. Now, one question we want to ask and answer is, what makes the CPI to go up? Or what makes, as a layman, we can say, what makes our CPU to perform poorly? And then one thing we have to know is CPU almost never achieve its ideal CPI, which is 1.0. Mostly it doesn't achieve that because of real world execution frictions. There are some frictions when we are running a program or when a program is running on our machine. There are some frictions which will come out, which will prevent the CPU not to function as intended. One of the friction or one of the bottleneck is structural hazards. So one of the reasons why the CPI will go up is a structural hazards. So when we are talking about structural hazard, it's about 2 instructions needed the same CPU resource at the same time. So one has to wait, and that creates an idle time, or that will make the CPU to stop. And then the second friction or the second bottleneck is data dependencies. Data dependencies is, let me give this analogy. Let's say a relay marathon. Well, one runner will have to wait for the other runner to bring the stick so that he will start running. So when we are running programs, if one instruction depends on the result of the other instruction, then that instruction will have to wait. If, let's say, instruction B is waiting for the result of instruction A, then instruction B will have to wait for A to finish. And this will create friction. In that case, probably the instruction A is having a long running process, or it's not quite fast. So that will create friction or bottleneck for the CPU to be slow. The last one, which is the biggest one, we call it memory latency. Memory latency is generally the CPU is faster than the RAM. The CPU runs faster than the RAM. And then if the CPU needs data from the RAM and then the RAM is not ready, then the CPU will have to wait for it to be ready then before the data can be fetched. That is what we call memory latency. developers, improving performance often means keeping related data close together in memory, which reduce CPU stores. Keeping data closer in memory means we have to look at how we structure our data structure. Maybe related data, we can put them in arrays, and then those particular data will become closer to each other. So when one data is fetched, or all of them could be fetched at the same time, which will increase the CPU performance. For a faster program, our goal is to have a lower CPI, a higher clock speed, and then a low instruction count. That is our ideal goal. Lower CPI means fewer instructions per second, and then higher clock speed is about more cycles per second. And clock speed can skew clock speed through the CPU itself, like the cores and the threads. So we can skew clock speed using the cores and the threads. And then we also want lower instruction count, which is what? Doing the same work with faster instructions. Doing the same work with fewer instructions. So overall performance improve when we lower CPI and then we increase the clock speed. Also, when we also reduce the number of instructions a program needs. Now let's look at millions instructions per second and floating point operations per second. While we said that clock speed and CPI describe the internal mechanics of a processor, millions of instructions per second and floating point operations per second is all about measurement. They measure the output performance. They try to determine how much actual work the CPU is doing. But what we have to know is that these metrics or these measurements, we have to treat them with caution, since they don't always reflect the real world performance across different workloads and architecture. Millions of operations per second, millions of instructions per second. It measures how many millions of instructions a CPU can execute each second. Sorry for the delay. So MIPS measures how many millions of instructions a CPU can execute each second. One advantage is it gives a simple way to express a processor's raw speed. And it is also useful when we compare similar processors. That is, when we compare a CPU of the same family but different generations. So we can compare Intel i7 from 2023 versus Intel i7 from 2024. So when we want to compare these two performance, then we can use MIPS. But there are some disadvantages. First, MIPS don't consider how much work each instruction actually does. A RISC processor may show higher MIPS because its instructions are simpler and quick, while a 6 processor might have a lower mix but accomplish more instructions. Another disadvantage is MIPS doesn't reflect a real efficiency. MIPS can be high even when the CPU is waiting or idle. So it doesn't always represent meaningful or useful work. Okay, so now let's move on to flops. With flops, we are talking about measuring the performance of GPUs and supercomputers. It measures how many floating point calculations a system can perform each second. Most GPUs are used to train AI, and then are also used in 3D rendering. So those applications, they usually use mathematical calculation. They mostly use mathematical calculations or decimal calculations. So the flops is a way to measure how often they do those calculations. And one advantage is it is a key metric for GPUs and supercomputers. But we also have disadvantage for flops. The first one is flops will not reflect everyday performance like the way MIPS will reflect for us. It won't tell us how fast a CPU can open a web browser or run applications like Excel, since those tasks rely on general CPU performance. In essence, we can say that MIPS impart latency or responsiveness, while flops would tell us the throughput of a CPU. If we are building a real-world system, if you are building a real-time system, or we are building a regular application, what we will care about is MIPS. We will need to know that the CPU can process many small logics in very short time frames. So we need to know whether the CPU can handle if-else statements and those small logics. So we'll care depends on how many mathematical calculations the system can handle in a second. So now let's talk about performance techniques as developers. How we can impact performance. So performance techniques are methods used to make systems run programs faster, more efficiently, and with better use of resources. Our aim is to improve overall performance, increase throughput, and optimize how effectively the system performs work. Sorry for the interruption. So we group performance techniques into categories. The first category, we call it the throughput engines. The first under throughput engine is pipelining. What is pipelining? Pipelining is about executing instructions or split instructions into different stages, like the fetch, decode, execute, and other. So with pipelining, it allows multiple instructions to be processed simultaneously. Then we also have parallel processing. Parallel processing uses multiple cores or processes to run different tasks at the same time. Then we have instruction level parallelism, ILP. ILP executes independent instructions from a single program simultaneously, even on one core. So with these techniques, a system which is having one core CPU, could perform or could operate as a dual core because it will execute independent instructions from a single program simultaneously. And then we have the superscalar processors or superscalar processing. With superscalar processing, the CPU will issue and execute multiple instructions in one clock cycle using multiple execution units. And the last one under this category is out of order execution. Out of order execution is about when the CPU will try to look ahead in a program to find whether there is an instruction which is ready. And the CPU execute that instruction, even though that instruction is not the one next in line. So far as it doesn't break the logic of the program, the CPU will try to execute that particular instruction ahead of time. The second category is about managing memory. It's about managing memory. We've learned that the CPU mostly runs faster than the memory. And then most of the times, the CPU will have to be waiting for data from the memory to execute program. So there are some techniques which are in place to prevent that. One technique is cache memory, using cache memory. Cache memory is a small, fast memory which is closer to the CPU, and it stores frequently used data to reduce the wait times between the RAM and the CPU. Then we also have the memory interleaving. Memory interleaving is when the memory is split into multiple modules. So the CPU can access different sessions at the same time. And this will increase the bandwidth or how fast the data flow. The last category we'll look at is the intelligent guessing category. The CPU will try to guess or try to use its brain for and predict what will happen next. The first one is branch prediction. Branch prediction. This is where the CPU guesses the outcome of decisions to keep execution flow and prevent stalls. Most of the time, most of the programs we will write will be like the CPU has already run that instruction before. So when it sees that particular instruction, it will try to guess the outcome so that it will prevent stalls. Another example is speculative execution. This one, the CPU goes further by executing the predicted path in advance before confirming whether it is correct. But the disadvantage is that if the prediction is not correct, if the prediction is not correct or is wrong, then the work is discarded and the CPU has to redo it again. Okay, so this is the end of our presentation. So for us to wrap up, we can say that CPU performance is not just about increasing the clock speed. It's not just about saying gigahertz and quad core or octa core. It is more about combining the capacity, which is the clock speed, and efficiency, the architecture and the software. So understanding this helps us to choose better systems, write faster and more optimized programs. Yeah, thank you. Okay, so please, if there is any question, you can ask us and then we'll try to answer. Thank you. Hello.
Hello.
Hello, sir. Please, we are done. Now it's question time.
Rogers, I think, can you hear me?
Yeah.
I don't think they have any question for now. So
All right. David.
Oh, yes. Oh, yes.
Hello. Yeah.
Please, can you hear me?
Yeah, I'm on. Yes.
So during your presentation, you made mention of what latency. So I want you to go back and try to explain what latency means. So I want to understand.
Please come again.
So you made mention of latency. Latency.
Okay.
So please, can you explain what it means again? I want to get the concept.
Okay. Latency is all about the time delay of a system responsiveness. So one particular example I can give is when you visit a website and you click, let's say, buy button, how fast when you click the buy button, how fast that buy button responds to you. Sometimes when you click it, you can be there and you see that there is nothing which is happening. So you click it again. So sometimes the moment you click it, then it responds to your your command. So that is all. I think that is all about latency. It's how fast a system responds to requests. I hope I'm clear. Hello, Ben.
Yeah, it's fine.
Hello.
Okay.
Is any other question for them? Okay, so if there's none, let's pick the next group, please.
So group 7.
Okay, group 7, we are ready. Please unshare your screen so we can share ours.
Yeah, I'm coming. All right, done.
Please, can you all see my screen?
Yeah, we can.
All right. Okay, so this is group 7. And I'm giving this presentation on behalf of all my group members. And we also chose the memory system to give our presentation on. This is a list of our group members. I'll mention our names after the presentation is done. My name is Ampo Fweje doing the presentation. This is our presentation outline. Introduction to memory system. Types of memory system. primary memory, which is RAM and ROM. Cache memory will get the speed versus the efficiency. Virtual memory concept, secondary storage solution, and then the summary and conclusion. So the memory system, the computer memory is defined as an electronic component of a computer system that is used to store data, instructions, and information temporarily or permanently for processing and retrieval. I hope this is self-explanatory because the memory is what stores data or the instruction we put onto the computer temporarily or permanently. And when we want to retrieve any information, it is the memory that helps us to do so. So we have types of memory system. We have the primary memory, virtual memory, cache memory, and secondary memory. The primary memory, which consists of RAM and ROM. The primary memory is the main memory of the computer that the central processing unit can access directly. It is volatile or non-volatile. Let me take it again. The primary memory, which is RAM and ROM, is the main memory of the computer that the central processing unit can access directly. It is volatile or non-volatile storage location that holds data and instructions for current program running. We have a picture to show the volatile memory and the non-volatile memory. Volatile memory. The volatile memory is a type of computer memory that requires a constant power supply to retain stored data when power is lost. All stored information are erased. What I mean is the volatile memory, it's what stores when power is constant, it is stored. After you lose power and restore power again, the information you have input, the data you input is erased. Example of volatile memory is the RAM. This is the characteristics of the RAM, which is the random access memory. The most common type of volatile memory. The RAM is the most common type of volatile memory. It holds data for currently running applications. Cleared when the computer shut down and restart. So this is what I meant by when you log on data and the computer loses power, your data is cleared. Example, when you open a browser or document, it is stored in RAM temporarily. Now we move on to non-volatile memory. Non-volatile memory is a type of computer memory that retains stored data permanently, even when the power supply is turned off. So unlike the volatile memory, here, when power is turned off, you still have access to your data. This non-volatile memory is essential. It stores the operating system, software, and user data. It preserves data when shut down, even when it's shut down. It provides permanent storage for future use. Example of non-volatile memory is the ROM, which is read-only memory. The read-only memory stores firmware. Example, boot program. It cannot be easily modified. That's a characteristic of the read-only memory. It is found on the motherboard. Example of non-volatile memory, we have pictures to show. We've displayed an example of non-volatile memories here. That is floppy disk, compact disk, internal hard drive, external hard drive, flash drive, and SD card. These are few examples. Another type of memory is the cache memory. The cache memory is a system part of a computer, which is extremely fast. The memory is located very close to the central processing unit. Its function is to speed up data access by holding copies of frequently used instructions and data from the main RAM. This is the cache memory. Now, details of the cache memory. The cache memory is designed to bridge the speed gap between the CPU, the primary memory, which is RAM. The CPU is very fast, while RAM is relatively slower. Cache stores frequently accessed data, so the CPU can retrieve it quickly. This improves overall system performance and efficiency. Cache memory works based on the principle of locality of reference. Temporal locality, which is recently used data, is likely to be used again. Then we have spatial locality. Nearby data is likely to be accessed soon. We have types of cache memory. The cache memory, the first type of cache memory is the L1 cache, also known as level 1. It's the smallest and fastest, located inside the CPU's core. It stores most critical data. The L2, which is level 2, larger than L1, but slightly slower. It may be inside or near the CPU. The third type of cache memory is the L3, which is level 3. Largest among cache levels. The level 3 is the largest among the cache memory levels, shared among CPU cores. It's slower than L1, L2, but it's still faster than RAM. Then the next is the virtual memory. Virtual memory is a temporary management technique that allows a computer to use part of its secondary storage, such as a hard disk, as an extension of main memory, RAM, enabling the system to run larger programs than the physical memory can support. This is what the virtual memory does. That's a picture to show virtual memory in operating system. So in operating system, this is how the virtual memory is. Explanation to the virtual memory. Virtual memory is used when RAM is not sufficient to hold all the data and programs currently in use. The operating system temporarily transfers data from RAM to secondary storage. This process is called paging or swapping. When needed, the data is brought back into RAM for processing. This creates the illusion of a larger memory space, hence the term virtual memory. The key concept, paging. Paging means dividing memory into fixed size blocks called pages. Swapping. Swapping means moving data between RAM and disk. And page file. Page file, space on disk used as virtual memory. Advantages. Allows running large programs. It supports multitasking. It improves memory utilization. And then the disadvantage of cache memory. Slower than RAM because disk access is slower. Can cause system lag if overused. Called trashing. We move on to the next type of memory, which is the secondary memory. Secondary memory is a non-volatile memory used for long-term storage of data programs. Its operating system, when are not in use and is not directly accessible by the central processing unit, data must first be copied into primary memory to be processed. Its purpose is to provide large capacity of data storage. This is the storage devices, computer storage devices, memory card, hard disk drive, floppy disk, pen drive, and optical disk. The secondary memory. Academic explanation. Secondary memory, also known as auxiliary storage, is used for long-term data storage. It is not directly accessed by the CPU. Instead, data must first be loaded into primary memory before processing. It plays a crucial role in storing the operating system applications and user files. It provides large storage capacity, preserving data even when the computer is turned off. That is the secondary memory. Then types of secondary memory. The first is magnetic storage. Uses magnetic field to store data. Examples: hard disk drive, is a magnetic type. Then example 2, type 2 of secondary memory is optical storage. Uses laser technology to read or write data. Example is the CD, the DVD, and Blu-ray discs. The third type of secondary memory is solid-state storage. Uses electronic circuits, no moving parts. Example, solid-state drive, USB, flash drive, and memory card. In conclusion to our presentation, memory systems are a hierarchy of speed and size. Primary memory handles active tasks. Secondary storage handles permanent data. Cache and virtual memory optimize systems performance. So the picture is depicting the hierarchy of speed and size. Thank you. Group 7, this is our presentation. Any questions, please?
Yeah, I have a question. Hello, can you hear me?
Yes, kindly allow me to hear from my group members if they are present, so they may be active to respond to the questions if I'm not able to.
Yes.
Do I have your permission?
Oh, go ahead.
Daniela Aninkra, she's our leader. Daniela.
I'm here.
And myself, I'm Pofweji. Andy Martins. I'm sure he's not around. James Shine Afenyo.
I'm here.
Safiu Abbas.
Hello, active.
John Kuntu Blankson. Daniel Amponsa.
Present.
Wisdom Dumont Toche Kudjo. Richard Tete.
I'm active.
Kasim Sharif Ewura. Nana Kwabna Sarkodie. Jennifer McCoy Tiyamo.
Present.
Francis Eugene Ekuban.
I'm
Maxwell
here.
Apia. Cynthia Akulago.
I'm here.
Prince Afo.
I'm here.
Emmanuel Nuoklo Kobla.
Present, I'm here.
Emmanuel Pra. Kelly Enoch Avuyi.
I'm here.
All right, so most of my group members are present. Kindly go ahead with your question.
So can you go to the slide where you had the paging and then swapping?
Right. Yeah, I have it. Please, can you see?
What is displayed now is virtual memory.
I have the paging here, key concept, paging, swapping, file, page file. Can you see, please?
Okay, I've seen it. So the paging, it says dividing memory into fixed size block called pages. Please, can you explain this concept a bit for us to understand what is meant by dividing memory into fixed sizes block?
So the paging comes from the virtual memory, right? And we are saying the key concept of virtual memory, we have paging, dividing memory into fixed size blocks called pages.
Hello?
Yeah, Shafi, kindly step in if you can explain better.
Okay, so like paging is basically how the computer manages memory when RAM is not enough. Okay, so what happens is that the system divides memory into small but fixed size parts, which are usually called pages. Then when the RAM is full, some of those pages are then moved from the RAM to the hard drive. Please, does it make sense? So instead of the computer stopping and crashing, all it does is it will just store some data temporarily on the disk to create space. Please, do you get it now? Or I've not clarified your question. Hello?
It's fine. The explanation is okay.
Okay, thank you.
Please, can we unshare our screen if there are no more questions? Okay, thank you, everyone.
Please, I have a question.
Okay.
Can I go on, please?
Yeah.
So on your slide, it stated that the cache memory bridges the gap speed between CPU and RAM. So I want to ask, to what extent can cache memory realistically reduce this gap? And are there architectural limits that prevent cache from completely eliminating the latency differences?
There's a question again, like what extent and what's the next question?
So I was asking, the next question, right? The next question is then, to what extent can the cache memory realistically reduce this gap? And are there architectural limits that prevent this cache from completely eliminating the latency differences?
Let's deal with the first questions first. So kindly repeat your first questions. Afterwards, you can bring in the second.
So I will say that on the slide, it stated that the cache memory bridges the speed gap between CPU and RAM. So to what extent can this cache memory realistically reduce this gap?
Okay, so like when we say like the cache memory bridges the gap, we basically mean it reduces the speed difference that's between the CPU and the RAM, but not to an extent, but not completely. Though the CPU is extremely fast, while the RAM is slower, the cache memory, which is much faster than the RAM, stores like the data, that's the used data. So the CPU doesn't always have to go to the RAM. So like it bridges the gap, but not entirely, not completely, to a larger extent. Hello, is that enough for you?
Yes, please. This is enough for me.
Okay.
Thank,
What was
thank
the
you very
next
much.
question? Thank you.
All right. Thank you, everyone. This is the end of our presentation, Group 7. Thank you.
Hello, sir. Hello, Doc.
Hello? Hello?
So it's left with only one
Hello?
group left. So we are left with only
Hello?
7. I don't know whether we can.
David, can you hear me? David? Hello, David.
No, I can.
Yeah, I think we have the last group, right?
Yes, please.
So let them take it, then we close.
Okay, because of the time, that's why I was asked. I'm asking.
It's time. It's time. Okay. What will happen? Okay. And next week, before I teach, we'll let them present briefly before I teach. Okay. Okay.
Okay, sure. Okay, sure.
Okay.
Yeah.
Okay, sir.
Yeah.
So can we present or we should be in next week?
Hello, David. David.
Yeah, can you
David.
hear me?
Yes. Please, can you reshare the various topics in which the group presented on the quiz so that we can get access to them?
Yeah, I will share it on the group.
All right. Thank you.
So if maybe there's no other question or queries, like we will call the meeting so that we prepare for the next class. Please let's prepare for the next one. Those who are yet will be doing their presentation today, please kindly prepare so that when it's your turn, we utilize the time. If not, we can't do anything after the presentation. So please kindly take it.